So here it is, Earth's climate. To give you a basic definition, when we talk about climate, what we're essentially doing is talking about weather, seasonal weather, but averaged over at least 30 years. So that sort of becomes the true definition of climate, long-term weather, seasonally averaged, and the average has to be a minimum of 30 years. And what we're really focusing on is temperature and precipitation. Now, we have to make sure that we're talking about seasonal averages because we can't use an annual average. That's not going to make any sense. If, for example, you live in the Rust Belt, your winters are awfully severe, but your summers can be awfully toasty. If you average those temperatures together, you might get something akin to San Diego, which doesn't make any sense at all because it's completely different. San Diego, of course, wintertime is closer in temperature and precipitation than with our summertime versus somewhere in the Midwest. But again, we still need to take a look at seasonal averages and seasonal variation. So again, think seasonal. When we take a look at Earth's climate, we can really break down the climatology into latitude. And as you see here in this particular climate map, we have latitudinal variations, which really becomes the strong part of our climate analysis. That makes perfect sense because we know that latitude is the biggest key when we're talking about temperature variations. We talked about the seasons before. We know that Earth tilt plays a big role in seasonal variation. We know that if you're along the equatorial zone, you're getting more direct solar radiation. Not only that, if you're on the equator, every single day of the year has 12 hours of day and 12 hours of night. Whereas if you're at a higher latitude, let's say Iceland, for example, at around 66 degrees north latitude, the amount of daylight hours you have broaches 24 because once you hit the Arctic Circle at 66 and a half, in the summertime, you're going to have 24 hours of daylight. And then in the wintertime, you can have 24 hours of darkness. That is just an amazing differentiation. By the way, I don't know if you guys saw or not, there's the recent season 3 of True Detective. And season 3 of True Detective, I think it was called Night Country. And Night Country was supposed to be based in Alaska. And throughout the entire show, it's nighttime in Alaska as they're solving these murder mysteries. They actually filmed it in Iceland because A, it's cheaper to film in Iceland. And then it's 24 hours of night in Iceland when they wanted to film it. So it just made more sense to do it out there. And oftentimes that'll happen. And I only say this and I only know this because I actually know someone who was on the show. Because when I go to Iceland, we have a tour guide because I go to Iceland almost every year for Northern Lights tour that I help conduct. And our tour guide is an actor from America who lives in Iceland. And whenever films or TV shows are made that's in Iceland, they always look out for local talent. And if they can find someone with an American background with no accent, that goes a long way. So this guy oftentimes finds himself in various TV shows that are filmed in Iceland. So he was in Night Country, True Detective Part 3. He was also in this Lifetime show, and I think it was called Love in Iceland or something like that. So really funny stuff. But again, if we look in Iceland, it's up here. And interesting to note that Iceland doesn't look like where it is that you would think it would be. You would presume that Iceland would be a polar or completely subpolar climatology, but you'll note here that it straddles in the temperate zone as well. And the reason for that is because you've got the warm Gulf Stream current that flows up to the North Atlantic, and it helps moderate the temperature of Iceland a bit. That's why parts of Iceland will be in the temperate zone and parts of it will be in this polar subpolar zone. But that's also why it's uniquely different than parts of Greenland, because Greenland doesn't get that nice warm water current from the Gulf Stream. That heads up here in the North Atlantic. So again, little differences that go beyond latitude, plays a role. You'll also note too that if we look here in various places of the map, being continental or coastal is also going to play a role in your climatology. And that's because we have specific heat differences when water comes to play. There's latent heat evaporation issues when you've got water come to play. There's temperatures of currents when there's water involved. And so latitude, intercontinentality, and then coastal currents are really going to play big roles in how those long-term climate zones are affected. Okay, with that said, let's take a look at a climate classification system which I adore called the Koppen Classification System. This was developed by someone named Vladimir Koppen of German ancestry and Russian ancestry, which has absolutely no bearing on our conversation, but just historically, it's sort of nice to know. And over the 18-year time span of 1918 to 1936, he created a climate system which focused on vegetation distribution. Vegetation, therefore, becomes the proxy for climate. And the question is, why and how did Koppen come up with this? Well, first of all, we can just take a look at these sort of rough photos here. Here are plants that live in wet environments. And plants that live in wet environments look a certain way. They could be leafy, big, broad leaf. They can have waxy texture on the leaf system. They can have thicker stems. They can have an interesting root system. But more importantly, they are going to look way different than plants that live in dry environments. Dry environment plants might be stuff like this: cacti, succulents, low-lying shrub, plants that don't have big fatty leaf. And again, the question is why? Because Vladimir Koppen recognized this. Well, let's take a look at a leaf. And I will try my best to draw a leaf. I draw leaves way better than people. Here's my person, and here's my leaf. You can see that the leaves are way better. Thank you. So when you have a leaf, and when we talk about photosynthesis, what is the plant actually doing? During photosynthesis, a plant is going to take solar energy, and it's going to convert that solar energy into a chemical form that everything that's living on this planet can use. So again, we've got solar radiation coming in. That's our solar energy. If there's water in the atmosphere, then H2O is also going to become part of this chemical equation. And then carbon dioxide, which is in the atmosphere, also becomes part of this chemical equation. So solar energy plus water plus CO2, this reaction takes place on the green pigment of the plant called chlorophyll, and the end result is going to be carbohydrates, sugars, glucose. So we'll just say glucose. And that is the conversion of the solar energy into a chemical energy, plus oxygen is a byproduct, plus some remaining H2O or water. And so this water is also a result. And when this plant wants to live, it reverses the equation, and the reversal of the equation is called transpiration. So the plant's going to use the energy, it'll use O2, it'll use the water. The exhalation, so to speak, of the plant is energy in the form of heat. Water vapor is also released, and then some CO2 as well in smaller margins. But you can see that during this process, water is shared by this plant from the plant to the atmosphere and vice versa. And so evapotranspiration, when the plant releases the water back into the atmosphere, is actually somewhat important. So we know already that this plant doing photosynthesis needs solar energy and it needs water. Let's say, for sake of argument, we took one of these leaves from a wet environment and we put it in a dry environment. And so if we do that, let's take a look at how everything is going to look. We're going to take a little leaf and we're going to stick it in a very dry environment. So actually, let me rephrase that because I'm going backwards. We're going to take a big leaf and stick this big leaf in a very dry environment. Now, again, the solar energy is coming down, photosynthesis is taking place. So solar energy plus H2O plus CO2 is going to yield us glucose, or we'll just say chemical energy. So Ce plus H2O is a byproduct plus oxygen. We don't have a lot of water though. And so if we've got a big leaf with a big leaf area index, which we call LAI, if the leaf area index is really big, then that means there's a big surface area for a lot of water to be evaporated from the plant. And if the leaf area is so big that the plant releases too much water, it's simply going to desiccate and dry out and die because it's going to lose too much moisture. Now, on the other hand, if we take a little leaf and we put it in a wet environment, so here's our little leaf now in the wet environment and it's raining a lot, and again, we look back at our photosynthesis equation, this plant is removing water, it's sharing water from the atmosphere, but it's raining so much, if the LAI is really small, and the leaf area index doesn't allow enough moisture to release itself from the plant itself is actually going to drown and die that way. So the leaf size is really indicative of how much moisture is in the atmosphere at that particular location. And that's why we begin to see that plants in wet environments look way different than plants in dry environments. And as a matter of fact, we'll talk much more about adaptations that plants have very soon. In addition to water, if you have a lot of sunlight and if you have a big leaf, then you know that you've got more surface area for photosynthesis. So it makes sense that a plant in a wet environment like a tropical rainforest zone, which has a lot of direct solar radiation because it's low in latitude, close to the tropics or the equatorial zone, will have a big leaf area index not only to remove a lot of water from the system, but also to have a big surface area for photosynthesis. You may say, well, it's a lot of sunlight in the desert. Why can't the leaves be big? And the answer is, again, because there's just not enough water. So if it does too much photosynthesis, it won't be able to release moisture because there's not enough of it. So it's going to desiccate and dry up. So again, the size itself is going to be not only indicative of amount of solar energy, but also, and in most places, moisture. And so if you were to ask me what's the most important variable to plants and plant growth, I would always lean on the side of moisture. That really is going to be an incredibly important variable to growth. Okay, so again, Koppen recognized this, and he made a classification system based upon what vegetation is where, and then from that classification system, we're able to determine climatology based on vegetation and vice versa. This is a very descriptive system. It's not critical. It doesn't explain any causes of climate change or climate differences. It only describes what climate is where based on vegetation. Very quick anecdote. I've been doing this for a minute. When I was in like year 3 at Southwestern College, as a matter of fact, we had a really cool education abroad program. And we had 1-month excursions to various places in the world. And one summer, Southwestern College was going to take a bunch of students to Italy. And they were looking for 2 professors to go to Italy with these students. And the goal was to teach classes that we offer at Southwestern College, but do them on site in Italy because we had a facility out in Florence, and just teach them content over there, but there had to be value of why you would teach that class over in Italy. So one of the people applying was an art historian, which made perfect sense. I will teach art history where David exists. So he got the job way easy. For me, What I did was I brought into an interview. It was an interview with a committee of like 10 people, and I had two photos. One photo was San Diego County, the other was Tuscany. And I put the photos in front of the committee and I said, tell me which is Tuscany and tell me which is San Diego. They couldn't do it because the pictures looked really, really similar. And then I showed them other pictures too of like Mount Vesuvius, but we won't get into that because the main point was the physical geography similarities and differences that we see around the world. Tuscany looks like San Diego, California. We are both Mediterranean climates, which means we both have the same climatology, which means our vegetation looks extremely similar. So that got me the free trip to Italy. And it was great. It was a month of my life. It was joyous. I had an apartment in Florence. I went with my wife. We didn't have kids yet. We had 4-day weekends every weekend for 4 weeks. We did take the students, though, to different places together, like Naples and Vesuvius. And then on the very last day before we were to leave, my wife had left at that point. She had family in Denmark. And so I told the students, I'm here on my own. I'm going to go to this island, Veen, and from there, I'm just going to spend the day on this tiny island. This was an island, by the way, where Napoleon was exiled to. So I go, I'm going to go to the island. I'm going to visit Napoleon's mansion. I'm going to rent a scooter and tool around the island. And that's what I'm going to do my last day. You guys do whatever you want. And I invited, though, the 26 students. And I said, if you want to come with me, you're more than welcome. But you got to meet me at 4 a.m. at the train station. So I go to the train station expecting no one, but there they were, 26 students waiting for me. Not a single one had even gone to their flat because they were out all night. Bars there don't close until super late slash super early. So they all just met me at the train station, and I literally spent the last day in Italy with all the students when I actually just wanted to spend it on my own. But that's okay. It was an absolutely beautiful experience. And again, that island was incredibly similar to an island like Catalina. So if you've ever gone to Catalina, that's what this particular island in the Mediterranean looked like. Very cool and a lot of fun. Okay, so this image here, again, highlights the whole concept of Koppen. A tropical rainforest zone is going to exist within a certain temperature tolerance level. And there's also going to be a certain amount of precipitation that goes along with that tropical rainforest zone. Here's tundra. Tundra is an incredibly cold zone. You're not going to take tundra and put it up here where it rains a lot. All you're going to get is a bunch of bog and swamp because tundra is low-lying shrubbery to a certain extent. And remember where tundra is. It's in the Arctic zone where you're going to get permafrost. And permafrost is permanent frost, which means you can't have a deep root system. So you're not going to have big, thick trees. So you can't take tundra and put it up in a bunch of rainfall because it's all going to die. So again, plants are going to live in a certain precipitation and temperature tolerance zone. Here's the temperature rainforest or the temperate rainforest living in this particular zone. Temperate forest in this zone. Here's the tropical savanna with a certain temperature range and a certain moisture level as well. So again, this is what we see. Vegetation across the planet is really predictive based upon temperatures and based upon annual content or amount of precipitation. So let's take a look at a more deeper dive of the Koppen system. So here it is. Koppen divided the world into 5 major climate/vegetation zones. And again, note their very close proximity to latitude. Here is a climate zone. This is our AF zone or tropical rainforest. Surrounding the tropical rainforest is an AW zone, and we'll talk about this soon. And surrounding the AW zone is a BS zone, which is a semi-desert or semi-arid zone. And then surrounding that zone is a BW zone, which is a big desert. In other words, when you take a look at Koppen, It is distributed from the equatorial zone, then it goes north and south, and it follows this scheme of A through E. You're not going to go from A to C or A to D. There is transition within the climate zone. One of the questions on the study guide was, what is the Koppen climate distribution starting at the equator in Central Africa and then going north or south? And what I just said is exactly it. It'll start with AF, it then goes to AW, it then goes to BS, it then goes to BW. And that gets you through Africa, whether you go north or south. This is how climate's going to be distributed. So we'll talk about each one of them in a little bit more detail as we proceed through this particular lecture. But a tropical zone, an A zone, means that the temperatures are greater than 64 degrees Fahrenheit for all months of the year. When you get to a B zone, the most important element of the B zone is not temperature, but it's moisture. In a B zone, potential evaporation is greater than precipitation, meaning it don't rain that much. So B zones are dry. And your B zone, your dry zone, can be here, which is around 30 degrees north and south latitude, which are subtropical high pressure belts. But also look here, you've got these inland deserts. So again, the whole concept is it dry or not? And that would be a B zone. A C zone is a mild mid-latitude. And these are all C zones here along the Mediterranean. And we see our C zones down here as well, although not particularly well in this picture. And then you'll see C zones here as well, and here as well. And in a C zone, your temperatures are 27 to 64 degrees. That's your coldest month, and your summers can be hot. Then when you get to higher latitudes, you'll hit your D zone. And in your D zone, which is your severe mid-latitude, your coldest month now can actually be less than 27 degrees Fahrenheit. It gets super cold. And summers here are typically mild. Now I want you to pay close attention to this map. You'll notice I pointed out D zones here in the northern hemisphere. What I did not point out were any D zones in the southern hemisphere. Now, you might be saying, well, what's this? This little block here, that's actually on the Andes Mountains. If we look at where D zones are supposed to be in terms of latitude, it's right here. And it's right here. So these are the D zone latitude. But here, you don't see any D zones because it's all water. So again, severe mid-latitude, coldest month is supposed to be less than 27 degrees Fahrenheit. Because we don't see land masses here, we're not looking at any Ds at sea level in the southern hemisphere. But with that said, you can get D in the southern hemisphere, but you got to climb a mountain. And we'll talk about that soon. Okay. And then finally, we have our E zones, which is polar. Polar zones are way up here and way down here. And in a polar zone, the temperature is less than 10 centigrade or 50 degrees Fahrenheit for every single month of the year. It's just extraordinarily cold all year round. And then we have highlands, which I've alluded to, which I'll talk about later on at the very end. Okay? So what I want to do is go through each one. I don't think it'll take particularly too long, but please stop me if you have any questions, and I'm happy to answer them. But when we do this climate section, Koppen especially, our focus really is on biogeography to a certain extent, because we really want to see how biomes change dependent upon where you're at. And that's why I have this vegetation map up as well. But of course, the vegetation map and the Koppen map are very much identical because, again, Koppen is all based on vegetation anyway. So it makes sense.
When I was first reading it, I thought it was interesting that it was organized first from wet to dry, which seemed very extreme. Like
Yeah.
why would you have the most extremes right next to each other? But now that you explained it with the map that way, I can see it. It was just interesting to notice that that's what ended up being the order.
Yeah, and it's all transitional. So it just goes from wet to dry. So, and in fact, when we take a look at the A zones a little bit more detailed, you'll see that as well because we'll focus on that map. Now, this is a chart that we have on our Canvas site. When you're taking your examination next week, certainly have it by your side. And it describes all of the Koppen zones going from A all the way to H. And then it breaks them down into further detail. And there's other little letters that are attached to Koppen. I'm not asking you to memorize it, but to be perfectly honest with you, as you go through this, it's actually quite easy to memorize. Whenever you see a little F, it means that there's no dry season. And whenever you see a little M, that's monsoonal, it means there's a short dry season. And whenever you see a little W, that means there's a winter dry season, so it's tropical, wet, and dry. If you see these little letters anywhere, they mean the same thing. So right here, it's humid subtropical. There's our little F. There's our little W, and it means the exact same thing as up here. And then when you see a little A or a B, we're talking about hot summer, dry summer, warm summer, etc. But we can break Köppen down into finer detail. It's almost like using a decimal point on a big number. We can get more precision when we break it down using these other letters. And so we're going to break it down in our conversation, but again, feel free to use this on the exam and also feel free to use this map on the exam. This map is super informative. It breaks down the world into Köppen in really good, fine detail. What I just mentioned too with our Africa zone, here's AF, AW, BS, BW, and you can see that here on the map. And again, it just breaks it down into finer detail, and it describes it all here as well. So this is a really nice map to have by your side also. Okay, let's take a look at A climates. Now remember, A are AF, AM, AW. AF, AM, AW. AF, AM, AW. And you'll note that AW lands on the tropical savanna. And that's where we find the Sahel, for example. And so remember what the Sahel is due to. It's due to that shifting, that seasonal shift of the intertropical convergence zone. But again, this is how we see the distribution of A climates across the planet, very much tropical. And again, here's Indonesia, and you can see that it rains a ton out there, and therefore it's going to be AF. And again, with the F, that little F, it means there's no real dry season. Okay, so let's take a close look. Again, tropical wet AF, tropical rainforest climate. Monsoonal is AM. And when we look at monsoon, there is that wet dry season. Also due to the shift of the ITCZ, it still has dense forest like an AF zone because the dry season is short. So it's not long enough to have enough moisture stress to really limit how much growth occurs. It's not a big limiting factor. But when you get to the tropical wet, tropical dry zone, AW, now you've got tropical savanna. And I'll show you, well, here's tropical savanna right here. And tropical savanna is stuff that, of course, we see when you watch National Geographic. These are all the wildebeest, as we call them, food. So this is food on the African plains, but you'll notice that it's grassy lands interspersed with trees and shrub. That's unlike the tropical rainforest, which is extremely dense. Lots of foliage, lots of flora, lots of fauna. As a matter of fact, 1/2 to 2/3 of all species in the terrestrial plants and animals live in tropical forests. Again, let me repeat that. 1/2 to 2/3 of all the species on this planet reside in the tropical forest, in particular, the tropical rainforest. It's heaps of vegetation. So much so, as a matter of fact, that you'll have trees out there You'll have a very thick canopy. As a matter of fact, here's your ground. Ground space is a commodity because there's so much foliage on the ground as well that you'll even have plants called liana vines. And lianas are basically dangling on root system and branches of other trees, and their root system is dangling in the air because there's no ground for them to plant themselves on. So they're going to grab nutrients and moisture from the atmosphere itself. It's crazy. Now, this leads me to a question. What happens to the rainforest area if the forest is destroyed? Destroyed is a tough word. Let's say cleared. Let's say we're going to chop down some trees and use those trees for building. Let's say we're going to chop down the trees and use that area for farming and ranching and agricultural purposes. What happens when we chop down the rainforest? Now, if I were to ask you that question and you wouldn't really know a whole lot, intuitively speaking, you'd say, I don't know, but it must be pretty good for agriculture because there's got to be a lot of nutrients in that soil. Otherwise, how can all this stuff grow? Well, there are three elements to an ecosystem. One element is called your abiotic elements or your abiotic variables. That's non-living. So we're talking about water, sunlight, wind, anything to do with non-living is abiotic. The second element of an ecosystem is your biotic content. And your biotic content is anything that's living. It could be bacteria living in the ground. It could be worms, insects, animals. Anything living is a biotic element of an ecosystem. And the third, and oftentimes overlooked element to a ecosystem is detrital or your decomposers. A decomposer, for example, will be things like bacteria that are living in the soil. And what decomposers do is when a leaf, for example, finds its way into the ground, decomposers will come along, eat up some of the nutrients, break down the leaf. The leaf itself blends into the soil now and makes a mulch, and that puts nutrients back into the system. Decomposers are hugely important, especially in the rainforest. And the reason is the rainforest has so much plant life, flora, that when a leaf again gets pushed into the ground, decomposers come along, decompose the leaf, the nutrients get back into the system, those nutrients then get to feed plant life and animal life, and so it just feeds the entire system. Without decomposers, we wouldn't have a rainforest. Now, why is this important? It's important because the fact of the matter is soil in the rainforest is actually nutrient poor. Let me repeat that because it's completely counterintuitive. Soil in the rainforest is nutrient poor. And it's nutrient poor because there is so much life there sucking up the nutrients. In addition to that, it rains a lot. And when it rains a lot, water is going to leach through the soil and take away nutrients that might be at the top with it. So, let's say you've got a rainforest with a bunch of trees, a very thick canopy. Here's your ground. Sun is shining. There's also a bunch of rain as well. That's your tropical rainforest. You chop down the trees. So now you're left with this. And maybe some rain as well. And no more trees anymore. So the water's going to come down and any nutrients that might be left behind are going to leach away. In addition to that, any ions that you might have in the ground is going to combine with water, and that's going to yield you rust, iron oxide. So now you're going to get rust that's in the ground. Then the sun's going to come along and it's going to bake it. And so now the ground actually gets baked. And it's a hard panned baked soil. and it's called laterite. So if you chop down the rainforest, you're going to get laterization and turn the ground into laterite. It's rusted, it's hard packed, it's like a brick. Nothing is going to grow in that laterite. And so when we take a look at different places in the world, like the Amazon rainforest, and we see chopping down of forests for various reasons, that's actually affecting global climate. Because remember, our plant is participating in photosynthesis. It's a sink for carbon dioxide. And in addition to that, we have a certain albedo or amount of reflectivity in the rainforest because of the vegetation. So you chop down the rainforest, you no longer have a sink for CO2. The albedo is going to shift as well, reflecting more radiation or absorbing more radiation in certain areas, and that's going to heat up the system. So this is a global phenomena, chopping down the rainforest. And again, intuitively speaking, you would think, oh, I'll chop it down, the stuff will grow back fast, no problem. It doesn't work like that. The whole primary to secondary succession process, which you've probably read about, it takes hundreds of years for the rainforest to fix itself. This is actually a big problem. So deforestation is the real deal. And if we see it in places like the Amazon and the Congo, that's a big problem because it doesn't correct itself very quickly. And let me just give you an example too. And this is not the rainforest, this is Iceland. So Iceland is devoid of trees. It's mostly tundra. And you're thinking, well, that's odd, Ken, because you just told me that it's in a subarctic zone. In addition to that, there's a temperate element to it. Shouldn't it have trees? And the answer is yes. But hundreds and hundreds of years ago, when the Vikings landed on Iceland, they did a lot of clear cutting. They chopped down a lot of trees for wood fire, for burning, obviously to keep them warm, and to construct homes. Today, when you go to Iceland, it's devoid of trees because left to its natural devices, trees will grow back, but it takes a super long time for that to happen. And so what the Icelanders are doing right now is they're actually planting trees in various places in the hopes to expedite growth. And so you'll see very manicured forests in Iceland, and those are all man-made. They've all been planted, those trees. Now, this is Iceland. It's not the temperate rainforest or the tropical rainforest climate zone. So again, it just goes to show you that when you chop down trees and the soil is not amenable to that kind of growth right away, it takes a really, really long time for things to fix themselves. So this is actually a really big deal. That's why I'm spending a little bit of time on it. Deforestation is actually quite important to the global economics of heat exchange. And we want to keep that in mind. Okay. Beyond AF and AM, we do have our tropical AW zone, which is our wet and dry. And again, this is due to the seasonal shift of the intertropical convergence zone. In the summertime, that ITCZ is shifting northbound, so our low pressure system's up here. And in the wintertime, it's shifting southbound, so the low pressure is down here, and the Sahara endures the high pressure zone. So this area here is going to have a wet season, which is the summer, and a dry season, which is the winter. The vegetation, again, are grasses interspersed with trees and shrub. That's because the moisture stress is higher. You do have recurrent fires, by the way, that are natural, but this actually assists in regrowth. And it's called a secondary succession process where recurrent fires burn away dry shrub, get it away, and it encourages faster growth. So those are actually important. And then we do have our laterite soils out there in the tropical savanna. So again, this is the Sahel. It's also known as BSH because that's our semi-desert or semi-arid. So there's a lot of crossover between AW and between the semi-desert. And we certainly see that in the African zone. Okay. Any questions on this at all? We're going to talk about plants in just a second, specifically in the B zone, but there's a lot of plants in the AW zone that share a lot of B-type plant characteristics because keep in mind, whenever you have a dry zone, a plant is going to need to adapt in order to live in that dry zone. It's just too dry. So if a plant can't figure out a way to adapt to low moisture, it's just going to die. So a lot of the plants like low-lying shrubs, chaparral, grasses, they're all desert adapted because they don't need that much moisture. But then you'll start to see plants called succulents, which I'll get to in just a second, where succulents retain moisture in their tissue and then they can secure it and save it for another day. So again, these plant adapting plants are really quite clever. All right, so let's take a look at those dry climates. Dry climates occupy about 30% of Earth's land surface. And you see here, here's some big ones, the Sahara Desert, the Great Victorian Desert, Mojave, like we've heard of all those before, the Chihuahua Desert. These major deserts are found along the subtropical high, which again is right around 30 degrees north and 30 degrees south latitude. And those deserts are again due to the subtropical high pressure belt. So high pressure air is air that's being forced down. It's generally hot, but again, the definition is because it's dry. Now, the other forms of plant or desert conditions are BS, which is a semi-desert transitional zone, also known as steppe. And again, this is very, very close to an AW zone. It's a nice savanna. The subtropical deserts are extreme deserts. You put a capital W with that. And again, those capital W's are deserts. They're not semi. The capital S is the semi. When you put the little H next to it, it's indicative of the subtropical high. When you put the little K next to it, it's more intercontinental. So we'll just say inland. Okay, so again, just definition. So BH, again, are influenced by subtropical high. BK, by extreme continentality and or rain shadow effect. All right, so what about the desert plants? They are xerophytic in nature. Xerophytic is desert adapted. So let's think about that for a second. What kind of adaptation would a desert plant need to have? Well, one, a lot of these plants are going to be succulent. And again, a succulent is a plant that retains moisture in its tissue. An obvious choice would be ice plant. We have lots of ice plant out here. Ice plant is that triangular looking plant leaf. Looks like a triangle. And if you break it open, a bunch of moisture comes out. So it holds a lot of moisture in its tissue. By the way, these ice plant, they also have a really curious root system that is super intricate. And again, what these roots are doing is they're looking for water. So you might have a shallow root system. It's staying close to the atmosphere because it's looking for water. It's an intricate root system because it's looking for water so it can go really far. And they're really tolerant plants, which means they can undergo a lot of stress. And I'm using the term stress because plants undergo stress. If there's not enough moisture, that's a moisture stress. If there's too much noise, that's a noise stress. As it turns out, ice plant is very adaptable because it tolerates a lot of stress. And so where do we see a lot of ice plant? We'll see them on the side of freeways. Because when you grow the ice plant on the side of freeways, like take 805 and go southbound, you'll see ice plant all over the place because ice plant can endure a lot of stress. So freeway living is stressful. There's noises, there's some pollutants in the atmosphere, there's lack of moisture oftentimes. And the ice plant is a perfect plant to put on the side of the freeway because it keeps the slopes in place. You're not going to get a bunch of slope runoff because the ice plant itself, the intricate root system, is going to keep it in place. So that's a really nice adaptation. You're also going to see some plants that have deep root systems. And again, those plants are looking for water. So what the adaptation is plants are looking for water. You'll also have plants with very small leaf to no leaf, like a cactus. Again, anything you can do to save moisture, that's what the desert plant is going to do. One of my favorite adaptations is called CAM, or crustulation acid metabolism. This very ugly plant right here is called a welwitschia. And contrary to popular belief, this picture is one of a live welwitschia. It's not dead. It just looks that way. That's not its adaptation, though. Its adaptation is how it conducts itself during photosynthesis. Keep in mind, what are you lacking in the desert? You're lacking moisture. There is constant moisture stress in the desert. What do you need for photosynthesis? You need solar energy plus moisture plus carbon dioxide. Those are the elements or the ingredients that you need for photosynthesis. There's an abundance of solar energy if there's no clouds in the sky, but there's not an abundance of H2O. So doing photosynthesis during the day is not particularly efficient for the plants in the desert, but that's when solar energy is available. So what the welwitschia does is the following. It'll absorb solar energy during the day, and it'll store the solar energy within its tissue. As it turns out, the tissue, the leaf structure is slightly different in the CAM plant than in the regular plant. The CAM plant has a C4 structure. The regular plant is a C3 structure. Without going into any gory details, it's different. And because it's different, welwitschia is able to absorb solar energy during the day. Then at night is when it completes the photosynthetic process and does its photosynthesis. So welwitschia does photosynthesis at night, which is absolutely bizarre. Okay, so here's the next logical question you should be asking. There's more moisture at night? And the answer is actually yes. Remember, we got to go backwards now and remember some of the stuff we chatted about before. When we look at something like relative humidity is the moisture content in the atmosphere divided by the moisture capacity of the atmosphere times 100 to make it a percentage. Content is content. Whatever moisture there is in the atmosphere, that's the content. Capacity, though, is temperature dependent. So when temperatures go down, then capacity of hold moisture goes down. When temperatures go up, capacity of atmosphere to hold moisture goes up. Well, in the nighttime, temperatures are dropping. Capacity is dropping. And when capacity drops, then relative humidity goes up. There is more humidity at night available for the plant to use in the desert than during the day. That is why crustulation acid metabolism can occur. It is one of the more fascinating adaptations of a plant to do photosynthesis at night versus during the day. Pretty crazy stuff. Any questions on that at all? All right, cool. Let's take a look at C. We're going to skip the map. You guys can look at these maps, but again, here's a nice map. We've already talked about it. Here's the desert zone. Here's the steppe or the semi-desert. And again, it just makes sense because everything flows with Koppen. It's transitional. It's transitional this way and this way. It's transitional this way and this way. Whenever you go from a BW, you're going to be going to a BS first and vice versa. It has to be transitional. So these are going to be border climate zones, no doubt about it. Then after that, that's when you segue into your C zone. Okay? Which leads us to C, mesothermal, mild mid-latitude. We have variations of C. You've got your Mediterranean zone, which is your dry summer. And when you have a dry summer, you put a little S in there. When you got a little A, it's a hot summer. When you got a little B, it's a warm summer. San Diego predominantly is CSB. Okay, but let's draw this picture. Here is, oops, I don't want to draw the United States of America. I want to draw San Diego County, which is like this. So here's the county. Um, here's us at Palomar. And in Palomar, we're predominantly CSB. Well, actually, let me draw it this way. Here's Palomar right around here. You're a CSB. Getting close to a CSA can get really hot in San Marcos. It's a little bit inland, but not that far. Down here in Chula Vista, where I live, we're right around here. We're a little bit closer coastal, but we're also CSB. Now, if we start going inland, what are we going to get? We're going to hit the desert. We start hitting Yuma. That is a BS. So we hit the semi-desert. And then if we keep going east to Arizona, we now are going to eventually find ourselves in the BW. And in fact, Death Valley's on the way. So that is the transition. So it's not just going north and south, but it's also east and west. It's just transition. Humid subtropical, CFA, CWA, and again, the F is there's no dry season. The W means there's wet dry. But where do we find humid subtropical? Well, let's take a look here. Florida, for example, would be humid subtropical, just simply because there's a lot of moisture, and it gets a lot of moisture because of this Gulf Stream. So this affects temperatures, whereas we have the cold water current coming from Alaska. So that's one of the reasons why we'll be a little bit different. We're going to have a dry summer, and excuse me, we're going to have a dry year mostly versus the wet years mostly because of our currents are a little bit different. And then there's Marine West Coast. It's CFB, CFC, cooler summers now, and we find these BCFB or CFC zones right up here. Big Sur, the redwood forest. We've got that cold water current coming in. There's a lot of evaporation occurring. We've got a lot of fog and moisture up there. There's so much moisture, as a matter of fact, that we can feed our trees. If you're a big redwood, you need a lot of moisture, and we get a lot of that moisture along the Marine West Coast. And again, a lot of that is not only due to this cold water current, but due to low pressure system from the subpolar low that we find up here. And then, of course, we have our cold front systems that generally are generative starting in this particular zone. All right. 30 to 60 degrees of latitude, again, is mild. Little to no snow cover. That's our C-type zone. Oops. This is our C-type zone. Mediterranean, where we're at, CSA and CSB, we have a lot of chaparral, low-lying shrubs, olives, grains, grapes, citrus. I always like to focus on olives and grapes. And again, going back to Italy, one of the days I was in Italy in Florence, I went into a little liquor store. I was just going to get a bottle of Chianti. And sitting right next to the bottle of Chianti was a California Red. So it's California Red. The climate's similar. So we have olive, chaparral, grains, grape, citrus. So does Italy. So does France. So does parts of Chile. And I would care to argue that we've got some of the best in the world. We also, of course, have avocados, lots of them. They're not just in Mexico. We have avocados here, especially big avocado forests in Fallbrook, if I'm spelling that correctly. So big avocado ranches and farms up in the Fallbrook area. And again, it's all because of our Mediterranean climate. Humid subtropical has mixed forest, grasses, pines, rice, wheat, corn, tobacco, sugarcane. You might ask, well, what is a mixed forest? Mixed forest will have both deciduous or broadleaf and evergreen. And evergreen is typically conifers. So conifers are like pine needles, Torrey pines, deciduous broadleaf like an oak. Deciduous are seasonal, which means the leaves fall off in the fall and they grow back in the spring. So you're going to find a lot of deciduous, for example, up here, because again, the weather conditions are so extreme. Winter is way different than summer. So when the leaves fall off in fall, it's in preparation for winter. It's inefficient for the tree to do photosynthesis in winter, so the leaves fall off and it conserves energy. Then after that is spring, and the leaves grow back in preparation for summer for photosynthesis to be effective. Evergreens, on the other hand, are non-seasonal. So there's really no growing season and dormant season. It's just throughout the year. So in San Diego, we'll see a lot of evergreens. And we'll see cam plants like welwitschia. We'll see some deciduous, but not a lot. If you go to the CF or CW zone, that's when you start to see the mixed forest, and you'll see both of them together more often than not. A lot of our deciduous that we see out here in San Diego are actually man-made, man-grown. When you go to the pure CFA, CWA, those are natural. And then finally, our marine west coast, like I mentioned, you go to Big Sur, for example, Monterey, California. It's extremely forested, lots of greens, fruits, wheat, rye. So again, where you're at, vegetation and agriculture are going to change as well. All right, couple more, and then I'll let you guys go. The Lakers are playing tonight, yes. So if you got the Laker game, they're playing the Philadelphia 76ers. So now you've got your night all set.
Is any of module 6 going to be on the test?
Which one is module 6?
Biogeography and
Yeah,
soil.
yeah, biogeography will be on it as well. It's somewhat limited, but in our conversation this evening, we're talking a lot about biogeography. And thank you for asking that. The notes I have online, if you've seen those notes, it's 96 slides. That's way too much, and my apologies to you all. I'm going to shift that out and I'm going to replace it with a more abbreviated set of notes, which is much smaller. And the focus is really going to be on just the definition of ecosystem. Um, we'll look at trophic energy levels. It's all fairly simple stuff and very foundational and fundamental. But there will be a few questions on the exam that talk about biogeography, but only a few. Most of it is still going to be concentrating on the Koppen system.
Okay, thank you.
You're welcome. I like the Koppen system though too because we do segue into a lot of biogeography with our discussion of biomes and plants and the short discussion of ecosystems and decomposition. So we're sort of getting a lot of it here without having to talk about the biogeography specifically too much. But again, when you are looking at the biogeography content, certainly look at the definition of ecosystem, look at the trophic pyramids, because there's a couple of them, and just look at some of the adaptation slides, which are actually a lot of fun. So I ask, why does a whale look the way it does? And it's an adaptation to the physical environment to which it is in. So you'll have a couple of those questions, but it's all, again, pretty simple and straightforward stuff. All right, humid, continental, there's our D zone. That's our first look. Again, if we've got a little F, it means it's wet all the time. A little W is seasonal. Little a, B is indicative of a hot summer or a more milder summer. So here's our nice humid continental in the United States of America. And here we see it across Europe as well. Subarctic, we're going to higher latitudes now. So here's our subarctic zone. And it's a DFC or DFD or DWC or DWD. And again, the little C or D is indicative of a cool summer or a colder summer. Little F, it's wet all the time. Little W, it's seasonal. And again, take a close look. There is no D here at sea level in the southern hemisphere. Okay? Absent. We're looking at 40 to 70 degrees of latitude. You're going to get snow cover. Humid continental, there's about 40 to 55. Broadleaf deciduous, mixed forest as well. Grasses, it's the corn belt up here. Soybeans, hay, oats, and a lot of prairie lands. Subarctic is higher now in latitude 50 to 70. This is where we get our coniferous forest and our taiga. Taiga is a boreal forest, and boreal forest is a cold forest condition. So here's a nice boreal forest. And again, it's trees interspersed with grasses. There is a moisture stress, but more importantly, we're starting to get permafrost development, but we're not quite there yet. So it is species poor because of the harsh climate that does limit productivity and resilience. It's right that transition zone, that northern edge of the forest itself, the boreal forest. That cold, short summer limits growth of trees. A tree might be 4 inches in diameter, and that 4 inch diameter tree might actually be 200 years old. I mean, usually if you see a tree with a big trunk, you know that it's pretty old. And usually trees with smaller trunks or thinner trunks you would think are younger. But again, in the boreal forest, when you get to that taiga zone, there's a real limiting factor because of the temperature and the short summers. That's a nice picture of it here. And in fact, I like this. It's even better. I should send this to McGraw-Hill and say, here you go. This is a bigger picture, better picture. All right, so we go to E's now, is polar climate. Mean temperature of the warmest month is below 10 centigrade. Very little precipitation. It gets borderline desert. The two types of polar climate are ET, capital T is tundra, treeless. Lots of shrub though and moss. Very severe winters and cooler summers. Very high annual temperature range because remember, in the summertime, you'll get 24 hours of daylight, but in the wintertime, you'll get 24 hours of night. So it makes for extreme conditions. And then finally, we reach the ice cap. Capital F there means freezing, and we can call it an A as well, which is our Arctic zone. There's no monthly mean temperature above zero, permanent ice, permanent snow, and we have permafrost. And because you have permafrost, it's that permanent layer of frost beneath the surface. You just simply cannot have a deep root system. It just can't happen because you can't break through that frozen ground. All right. And then finally, we get to our highland climates. Highland climates have great diversity of climate conditions. They can be cooler and wetter than adjacent lowlands. And I think the best description of highland is variety and changeability. And let me show you this picture. This is a really cool image of biomes and mountain zones. And you really see some extreme vertical zonation. Now remember, when we were talking about Koppen in terms of latitude, we went from A to B to C to D to E. That's how Koppen works. It's just a series of transitions. The cool thing with altitude is it's the same thing. If you started down here in a C zone and then you went upward, then you're going to go to a D zone. And if you keep going even higher, you can go to an E zone. So let's presume that this is the windward side of a mountain. So here's our air flowing this way. And we know from previous discussion that if the air flows down the mountain, and this is the leeward side, it's now a high pressure zone, so the air gets compressed. So we start from an E, we can then go to a D, to a C, and even to a B if we're going down far enough, i.e. Death Valley. So again, the transition of Koppen works in altitude and it works in latitude. And so remember when I said there's no D's at sea level in the southern hemisphere, there are D's when you go to altitude in the southern hemisphere. So here's an example question you might see on the exam. True or false, there are D-type climates at the equator. At first, a student would say, well, that's false because the equatorial zone is A. But what if I go to the equatorial zone and I've got a mountain? And when I climb the mountain, I can certainly go up to a D or an E if the mountain is high enough. Mount Kilimanjaro, the Atlas Mountains. You can have D zones in the southern hemisphere. It just needs to be at altitude. So these are highland climates. Very fascinating. And it's funny, I spent 1 year of my life in Tucson, Arizona. I was going to the University of Arizona in Tucson. I'm coming from San Diego, and I'm not particularly used to the desert. I'm not enjoying the desert. I'm making up every excuse in the world not to continue at University of Arizona, but I'm going to suck it up and I'm going to spend the year there because I've already gotten student loans and I don't want to give the money back. So I stay in Tucson. I'm going to karate class 2 days or 2 times a day. I'm skipping classes. This is horrible because I'm a graduate student, but I know I'm not going to stay. I was not having a good time and I was missing San Diego. I was missing the ocean. But in addition to missing the ocean, I was missing pine trees. And you might say pine trees. Yes, because when I was a student at San Diego State, I actually have 2 degrees from there, 2 graduate degrees. The first one is astronomy, the second one is geography. So when I was an astronomy student, I would be at Mount Laguna Observatory all the time. I was doing star parties, I was doing some astronomical observations, some research. So I'm in Mount Laguna. And if y'all are familiar with Mount Laguna, you're going through Julian, then you're going up the mountain, and it's beautiful, and it looks like this. And it looks like this. So in Tucson, Arizona, there is a mountain, and it's called Mount Lemmon. And Mount Lemmon is not particularly high, but it's high enough to have snow. And so there's one ski lift in Mount Lemmon, and you can ski there, and it's sort of rocky skiing because it's not thick snow, but just enough. I would drive up to Mount Lemmon at least 1 day every single week just to remind myself of Mount Laguna and San Diego. You can do that when there's zonation, when there's mountainous highland zonation. So anytime I go back now to Tucson, which is very, very infrequent, but it's periodic, I'll take that drive up Mount Laguna. I mean, not Mount Laguna. I'll take that drive up Mount Lemmon and I'll get here to these trees and it just makes me feel good. It just reminds me of home. So there you have it. You can absolutely have D zones in the southern hemisphere, but it's just not at sea level. Okay. Does anybody have any questions about any of this stuff at all regarding Koppen? Because on the exam, it is a little bit Koppen heavy. There are some maps that are on the exam, and I'm asking you questions about those maps, and they're Koppen maps. And so that's why having This map and this chart by your side are probably going to be fairly helpful for you during the examination, but you just want to be comfortable with Koppen and the concepts and the ideas behind it and the relationship between temperature, precipitation, and plants. That's what you're really after. Okay. There was one more thing I wanted to share with you, and then I'll let you all go, so you can go watch the Laker game. Which actually I don't think it's on until like 7. You're fine. Um, on that announcement, I sent you some information about oxygen isotope analysis. And the genesis behind that announcement was, how do we know what the temperature profile of planet Earth has been over time? Like, how do we know what temperature was a million years ago, 2 million years ago? And in the slide deck, it talks about the various proofs that we have. And we talk about dendrochronology, which is really the analysis of tree rings. And if you've got a tree ring which is really fat on any given year, then you know that growth that year was really good. And if you got a particular species of tree, then you know what type of climate conditions that tree enjoys in order to grow. So by looking at the tree rings, you can actually interpolate what the climate was like X number of years ago. And getting to X is easy because every ring on the tree is indicative of 1 year of growth. You can do this with deciduous trees. You can't do it with evergreen. But that's sort of easy to understand. What's also relatively easy to understand is if we go to Greenland, for example, and we core out a bunch of ice, and if we look at the ice way down here and we date it to be like a million years old, and you might say, well, how do you date it to be a million years old? Well, that's actually not particularly difficult because trapped in this ice, you'll have air bubbles. And in those air bubbles, you might have, for example, trapped carbon dioxide, trapped oxygen, trapped methane. And this CO2 and this O2 and this CH4 were trapped in the atmosphere when this snow fell a million years ago. Those air bubbles were trapped, and over time, ice got more and more compacted with more and more snowfall. But we can actually age date the carbon in these molecules by using carbon age dating. And without getting into the gory details of carbon age dating, we can age out this stuff pretty well. And you'll also find various soil sediment samples trapped in the ice also, which you can age date. Okay, so why is this important? We can age date the air bubbles, right? But then you can also measure the air bubbles. If you've got a high density of carbon dioxide, and we know that CO2 is directly related to temperature, then we can interpolate global temperatures based upon carbon dioxide density or quantity in the trapped air bubbles. And we can in fact go all the way up through the column of ice from a million years ago to today. And we can make temperature profiles based upon CO2. As it turns out, and you can look in the other slide deck, I have graphs that look like this, where you'll see CO2 concentration changing over time. And we hit the industrial age and it just shoots up. But then we can look at CO2 being fairly consistent, but going up and down moderately over time, over like a million, 2 million years ago. And then you put the temperature profile on this same graph, and the temperature profile mimics CO2. Okay, so I want to dispel any type of controversy. If CO2 is rising, temperature is rising, period. I don't need to tell you where the CO2 is coming from. All you need to know is that when CO2 goes up, temperature is going up. When CO2 goes down, temperature is going down. It is that simple. So today we are seeing an absolute influx of CO2, principally due to the Industrial Revolution and humans purging too much CO2 into the atmosphere. Whether you believe anything at all or not, regarding global climate change, which is bizarre to me, but that's besides the point. You don't need to know anything other than the fact that when CO2 goes up, so too does temperature, period. And so, again, we can look at climate change and temperature from the past by looking at quantities of CO2 in the ice sheet. It's really that simple. But then I gave you one other. And the one other I gave you was oxygen isotope analysis, which may be a little bit confusing. So let me dispel that as well. Oxygen can come in various forms. There's O18 and there's O16. The 16 and the 18 are representative of mass number. So that is an indication of the mass of the oxygen atom. And when you've got an atom which has different masses, but it's the same atom, that's called an isotope. So your typical O16 is going to have 8 protons and 8 neutrons in the nucleus of the atom. And then surrounding that, you've got a valence shell of 2 electrons. And then surrounding that, you've got another shell of 6 electrons. So it's neutral. This is the structure of your O16. So the 16 is 8 plus 8, right? That's 16. O18 is actually the following. It's 8 protons because it's the protons which make the atom. 10 neutrons, surrounded now by 2 electrons, surrounded by 6 more electrons. 8 plus 10 is 18. So this is O18, and this one here is O16. Phew, why am I telling you this? Both O16 and O18 are found in nature. It just so happens that O18 is the heavier form of oxygen because it has 2 more neutrons in it, so it's heavier. So we call that a heavier element. It's heavier oxygen. Okay, so now let's put this in perspective. Let's say you've got a body of water. Here's H2O. In this H2O, some of the O's will be O18. Some of the O's will be O16. Both H2O16 and H2O18 evaporate. However, when it's cold, H2O16 evaporates more than H2O18. And the reason why H2O16 evaporates more than H2O18 is because it's lighter in weight. And because it's colder conditions, the lighter weight molecule is going to evaporate more readily than the heavier molecule. During hot conditions, both are going to evaporate at almost the same type of rate. But we're only looking at cold conditions at the moment. So in cold conditions, we're removing more O16 than O18, which means the quantity of O18 in the ocean actually goes up. Now, this water that's mostly O16 goes into clouds. It might go to land. It might snow. And we're going to enrich our ice with O16. So this is going to be ice. And then the ocean water itself is enriched with O18. This O18 is used to create seashells. So when you've got CO2 that's been evaporated or absorbed in the water, you add H2O to it, you add some calcium, you're going to get calcium carbonate, CaCO3. This is seashells. So your animals in the ocean actually do this process. They do the chemical process internally. They create the seashells themselves. When you've got very cold conditions, your O in the seashell is enriched with O18. And your ice is enriched with O16. Okay? So, if I have a cold condition, my seashell is going to have a lot of O18 in it. These seashells sink to the bottom of the ocean floor, get incorporated into the sedimentary record. And when they are deposited, if I have a layer here and it was deposited 1 million years ago and it was super cold, that's going to show in the CaCO3 because it's going to be enriched with O18. Then, when things start to warm up, this H2O, which has a bunch of O16 in it, melts. And when it melts, it flows back into the sea. I now purge the ocean with more O16, and now my CaCO3 is going to have more O16 in it. And so, a 500,000 years later, if I have another layering of CaCO3 shells, the CaCO3 now is going to have more O16 in it. So that's how we use oxygen isotope analysis. We can see it in the ice core with the amount of O16 in the ice core, and we can see it in shells with the amount of O18 in the seashells. So that's what that announcement was all about. It was just reviewing and reiterating how you can use oxygen isotopes to determine what climate in the past was all about. Okay?